Okay, so we will be covering. Uh, this you have already faced couple of times. Thinking of neurons as an RC switch, and we'll couple two of these, one inhibitory and one activatory, and see what happens. Then we'll consider a pool of them together, and then we'll do relax some of the constraints. So here you can see that the excitatory is in red and the inhibitory is in blue, but by mistake I've switched it. So whatever you see later, the red will actually be the inhibitory, like stop signal, and blue will be the excitatory. Cool. We will be using these tools. I think some of them have already been covered a bit, but whatever has not been covered, I'll try to make it clear. All right, so neuron as an RC circuit. So we have already seen this multiple times, neurons receiving input and then checking if it's above the threshold or below the threshold and turning on accordingly. And this is the dynamics of a simple RC circuit. So you have this minus C dV dt, dV dt equal to minus v equal to Vt by R, and that gives you this exponential decay of the voltage. Now if you put an external current, so I have taken these together, so RC I've called it tau, and accordingly I have so accordingly I have renamed the variables, and so you have tau di dt equal to minus I, what was before, what we had beforehand, plus the external current. So we inject a current in the system, and so what we see is it actually goes to a steady state at IE. It decays exponentially to a steady state IE. This you guys have already seen multiple times. So this you can also think of this neuron in lines of this, right, the switch. So here you have tau dxa dt similar to this, minus xa, so minus xa plus sigmoidal of whatever you're getting in. So instead of I external, I am considering the signal that I'm getting from my neighboring neurons or the neurons that I'm connected to, right? So at steady state, x will be sigma of x in, and so based on that it will be either be on or off. If x in is more than 0, it's on, x in less than 0, it's off. And so now if it's connected to a lot of them together, then the x in looks like this, right? So HA is the local field of your neuron A, and WAJ are the connections to the rest of the neurons, exactly like this, right? So the same idea, just explaining as through an RC switch. All right, now here there are a couple of parameters, and since we want to do an analysis, we would like to reduce the number of parameters as much as possible. Okay, before that, this RC using RC circuits as neurons have been, like, this is 1984 Hopfield's paper, where he used it to demonstrate that you can give memory. I mean, there's memory that you can have based on different resistances if you put, right? So the idea that I talked about yesterday, so Hopfield implemented it in an RC circuit, and so the governing equations were exactly the same, almost the same. So since we might be having a lot of parameters, we will consider a low temperature limit, so we can, like, divide it and absorb it into the step function, right? So what really matters, is it above 0 or is it less than 0? The actual magnitude does not matter. So essentially a step function like form is what we'll assume. All right, so what should be a minimal excitatory inhibitory single neuron coupling? Single neurons do not have, like, axons projecting onto themselves, right? So they won't have axons projecting onto themselves. They might be having some external field acting on them, and there will be cross coupling. So this will be the governing equation, right? So you have the usual decay term, and your input is essentially the cross coupling plus the input. Similarly for here, the decay term, and then a Heaviside, cross coupling, and the input external field, right? So that's the most minimal that we can come up with, right? So I don't have any parameters in front of minus v or u because I'm using this Heaviside function. So even if I have anything over here, I can just divide it and like absorb it, right? And it will make calculations much more easier, and we are only left with two parameters. All right, so what will the steady state be? U dot equal to 0 and V dot equal to 0, right? So which gives us u equal to step function of minus v plus hu, and v equal to step function u plus hv, right? Now if we solve this, we can use a integrator to solve this. Because of the step function, it might behave a little silly, but there are certain integrators which can handle it, and if we do it, we get something like this. It dies off after some time, and this is the phase plot. So this is the uv on the y-axis with different colors. The excitation variable is u, the inhibitory variable is v, just like what we have seen beforehand, and on this axis is time. So the fluctuation sort of dies off, and it becomes, and it goes to the 0.5. So the hu and hv parameter I've chosen to be 0.5 and minus 0.5. So realize one thing from here: u and v are u and v can either be from 0 to 1, right? And so minus v plus hu will, so the point at which it flips, the Heaviside function flips, is when minus v plus hu is equal to 0, right? So if you go, and that is v equal to hu. So if you're above, if your v is above hu, then this top Heaviside function for the u variable becomes positive, becomes active, the derivative becomes positive. And similarly for the inhibitory variable, the theta function will switch value at u plus hv equal to 0, and that gives us u equal to minus hv. So in our phase portrait, these are the two points where the switch will happen, right? And so this, you see, you can, like, it's almost like it's a null line, but yeah. So the blue over here, actually I realized Pranay had really nice figures because he could show arrows, but I've instead put these colors, right? So the blue is u in is greater than 0, and the red is v in greater than 0, right? So whenever the system is in this area, the u variable will start increasing, as that you see over here. So if you project it to the u axis, then you can see that the u variable is increasing. So this is the initial condition, and it starts from here. So as soon as it comes here, it increases only in the u direction, but in the v direction it's in the negative side, right? So this is the area where v dot is greater than 0. This is the area where u dot is greater than 0, right? So you see this pattern that, you start from here, only v dot is greater than 0, so it has a slightly right moving tendency, but u dot is less than 0, so it's going down. And then over here none are positive, so both are going towards 0. Then as soon as it crosses this null line, it shifts direction and it starts moving this way, and so you get this pattern. But why are we not seeing any oscillations? Because one is exciting the other is inhibiting the other. So for that, what we can try to do is, we have already found the fixed points, that is exactly at hu and minus hv. What we can try to do is do something called a linear stability analysis. So let me just give you a brief of what it is. Let's say we have two-dimensional ODE with these two as the variables, and they evolve according to this form, right. Now let the steady state, the fixed points, let's not call it steady state, the fixed points where x1 dot and x2 dot are 0 be x1 naught and x2 naught, right. So what I mean by that is f1 x1 naught comma x2 naught is equal to 0, which implies x1 dot is equal to 0. Okay, dot is d dt, and then f2 of x1 naught x2 naught is equal to 0, which implies x2 dot equal to 0. Now the idea of linear stability analysis is these are nonlinear functions, right, but what we can try to do is at the fixed point, it's at the fixed point, right. So if you perturb it a little bit, what is it going to do? So x1 equal to x1 naught plus some small perturbation, right. Similarly x2 equal to x2 naught plus some small perturbation, right. So why are we doing this? So that we can find what is, how stable is the fixed point, or this point x1 naught comma x2 naught, right. Right. So now we can plug this inside this, right. So we get x1 dot as x1 naught to dot. There are too many things. Dot is d dt, naught is the fixed point, right. And x1 and x2 are the two variables. So x1 naught dot plus delta x1 dot. Yeah, I am looking at this equation, putting in these values, right, equal to f1, and it's at this particular point x1 naught plus delta x1. Oh, these are not vectors, like I'm individually seeing them, and x, please point it out, please point out if you see any mistakes that I'm making, right.
If you don't point it out, I'll start deliberately giving you mistakes. Unless you warn them.
Right. Oh, so that's okay. So x2 naught plus delta x2, right. Similarly for this, at this point, which is like slightly off our fixed point, we have x2 dot naught plus delta x2 dot equal to f1 x1 naught plus delta x1 x, oh, see again, come on guys, x2 naught plus delta x2, right. Now x1 naught do, yeah, so I'm placing this inside this equation. So this will go out because from our definition there is 0, right, and so we will be left with delta x1 dot equal to this entire thing and delta x2 dot equal to that entire thing, right. Now the idea here is we are perturbing it very little. Now if you have a very little perturbation, let's say delta x1 equal to 0.001, right, delta x1 square will be, so this is 10 inverse 3, this will be 10 inverse 6, right. So all the higher orders will be extremely small, even smaller, right. Now what we can do is we can do a Taylor expansion of this, right. Any function can be approximated with the Taylor expansion. So that's what we do over here. So we have f1x equal to, I'm just writing the Taylor expansion form, so let me say fx equal to fx x naught equal to f of x naught plus dou f dou x, oh sorry, this will be delta x and this is x naught, yeah, dou f dou x evaluated at x naught into delta x plus all the higher order terms, right. So, we will just consider this part. Yeah. This is the linear part, that is where the linear stability analysis comes from, right. So, we do the same thing over here. So, dou x1 dot will have, now realize in this case it is 2 dependent on a single variable, but here it is dependent on 2 variables. So, I have to take into consideration 2 variables, right. So, f1 x1 naught comma x2 naught. So, differentiating with respect to the first variable will give us dou f1 dou x1 evaluated at x1 naught x2 naught into dou x1 at delta x1 plus dou f1 dou x2 delta x2 and plus the higher order terms, which I am leaving out because it is linear stability analysis. Then we have f2 x1 naught x2 naught plus dou f2 dou x1 delta x1 plus dou f2 dou x2 delta x2 plus the higher order terms. Realize that these two are 0, right, because of our condition that x1 naught and x2 naught are fixed points, right. So, these are 0. So, what we are left with is the perturbation near the fixed point x1 naught x2 naught will follow this equation dou f2 dou x1 dou f1 dou x1 delta x1 plus dou f1 dou x2 delta x2, and similarly for the next one, right. So, let me just replace it by I, right. Yeah, fair and clear till now, right. So, one trick that we can do here, it is 2 variable system. What we can do is we can write it in a matrix form, delta x1 delta x2 into A equal to dou f1 dou x2 dou f1 dou x2 dou f2 dou x1 and dou f2 dou x2. Yes. Right, and we have dou x1 dou x2. So, take a 5-second look at this and appreciate that this is just made into a matrix form. It is the same thing, like, so dou x1 dot will be dou f1 dou x1 delta x1 dou f1 dou x2 delta x2, which is the first one, and then the second one similarly, right. So, what is it actually? It is a linear equation, dou x vector dot equal to some matrix, which we usually call it, we call it the Jacobian in the literature, into dou x vector, right. What kind of solutions do linear equations give us? Huh? I mean x dot equal to Cx, what kind of straight line? Dx dt, right. So, dx dt equal to Cx, right. So, exactly. So, dx by x equal to C dt, and if you integrate it, you get ln x equal to Ct, and so you get x equal to e to the power Ct. Did I miss a minus anywhere? No, I didn't miss a minus. Okay, yeah. So, same thing, is just this is single variable, this is like a vector multivariable, right. So, what we will end up with for the solution is delta x vector will be exponential of something into delta x vector. Now, this something is a matrix, so exponential of a matrix. So, how do you deal with the exponential of a matrix? You diagonalize it, and that is what we do with the eigenvalue eigenvector calculation. You can diagonalize it into lambda 1, lambda 2, lambda 3, and you can multiply it with over that here, right. So this Jacobian, the eigenvalues of the Jacobian will essentially tell me is it unstable or stable. So if it's stable, then the eigenvalue of the Jacobian, one of like the eigenvalues of the Jacobian will be negative. Therefore, you will have e to the power minus something into a vector, right. And if it's unstable, the Jacobian will have a positive value. And what will happen if the Jacobian has a complex eigenvalue? Oscillatory, yes, exactly. So that's what we're going to do here. Right, so this is what the Jacobian is, and realize that the t I have reintroduced. So instead of the theta of x in, I have written it as sigma of x in, right, where theta is this step function, but sigma is this function, where sigma is essentially 1 plus 1 plus e to the power minus x in, right, by t. That is where the t comes from. So at t tends to 0, it becomes a step function, right. So this is in the limit t tends to 0 goes to the step function, exactly as this thing that we saw, right. The blue one is at finite temperature, the black one is at 0 temperature, right. So we have just reintroduced the t because taking t tends to 0 will mess up things, right, because there will be an infinity coming up over here, that is not very nice. So if you find the eigenvalues, you will come up with something like this. And so what is the real part of this eigenvalue? Minus 1, and so that tells me the dynamics will be stable and it will just go inside, right, and that is what we are seeing over here. Right, so what we can do is, like, this is another plot where in this axis, so this is a plot of plots, right. So each of these is essentially this picture, right, and in this axis I have varied hv, this axis I have varied hu, the two parameters that we have, and from that we can see that it never shows oscillation as we expect it, and it always always reaches the steady state at this minus hu comma minus hv comma hu, right. Okay, so single excitatory, single inhibitory didn't work. So let's put couple of them together, and so what do we have over here? A lot of excitatory and inhibitory, and each excitatory, which one is each excitatory is connected to all other except himself, herself, whatever, and each inhibitory is connected to all of them except itself, right. And so that's what we have over here. If you notice it, like give it a 5-second, 10-second glance, the usual bias term is there. Then we have these two terms, right, wij, ee, uj. So like similarly, like what I did before yesterday as well, you have this W matrix which essentially tells you who is connected to whom, right, adjacency matrix. The diagonal elements are 0. This is W u u, or excitatory, that is what I have written over there, excitatory connected to excitatory. This is W I I, this will be W E I, and this is W I E. So here excitatory receiving input from other excitatories, inhibitories receiving input from inhibitories, excitatories receiving input from inhibitories, and inhibitories receiving input from excitatory, right. So the way I will do it is x in, or if I may write, E in, I in, E and V, E I U V, same thing, all right. I have used it interchangeably. E means U, excitatory, I means V, inhibitory. So the input is equal to this matrix into your current state, of the system, right. So this is what we have, and this is what I have written it in equation. this is the input, right, of each of them. So you look at each of these excitatories, right, and that's what you get. So this is the equation for a single ith excitatory, this is the equation for a pth inhibitory, right? Clear till now with me? All right. Now the other thing is like this W, the weights I have chosen from a normal distribution, assuming that the connections are not always perfect and there will be some variations, yeah, and the HU and HV are also different in the sense that HU, the excitatory field is different from the inhibitory field, right? So this is the kind of thing that we see coming up, and so it turns out that it does work. You can see, so this is a kymograph, or Sumitra said raster plot. Can I call it a raster plot, because this is node index and this is time. So this is almost like state in this direction, time in this direction, and the shading essentially tells you is the zth, or like the third direction in which you essentially get how much activity there is. This is a time evolution plot, and this is a phase portrait. This is an averaged phase portrait, right? So where I have lumped all of the excitatories together. Oh no, I have messed up. This will be U and this will be V. This will be U, this will be V. The y axis in all the plots are excitatory, the x axis is inhibitory, right?
Does it matter?
There is no direction, you can't see direction. True, in phase portrait you can't see direction. Yeah, sorry. The kymograph tells you the entire system's activity, but you can see each individual node as well. Yes, just the activity, right? Like what is the U and V look like for each of the neurons. So this is this index, like neuron 1, neuron 2, neuron 3, neuron 4, and so on up to neuron NE plus NI. Right, NE is the number of excitatory, NI is the number of inhibitory, and then this is time. Sure. Yeah.
So we assume the matrix is symmetrical.
It's not really symmetric, but because yes, WIE, it's not symmetric because that's a crucial point. I'm sorry if I didn't mention. We are trying to model inhibition and excitation, right? So all the inhibitory, all the out degrees from inhibitory are negative, and all the out degrees from excitatory are positive, right? So here this excitatory is receiving input from excitatory and inhibitory, right? So when you're doing the matrix multiplication, E in will receive from this part and this part multiplied by E, this part multiplied by I, right? We want to conserve, we want to see the excitatory inhibitory dynamics, right? So this entire thing will be positive, this entire thing will be negative, right? Similarly, the inhibitory is receiving from excitatory and inhibitory, right? So this multiplied to this and this multiplied to this. So this will also be positive and this will be negative. Does that make sense? So this entire segment is positive. Yeah. Oh, I'm messing up the colors again, but I hope it's fine with you guys. And this entire part is negative. Yeah. So it's not symmetric at all. All right. Yeah. Okay. Now, how do we this looks rather cumbersome, like too many indices and too many variables. We want to arrive at some like simplified description of it. We are going to use this fact that all the weights are taken from a normal distribution. Realize this W, EI, W, E, EW, I, EW, II are actually all plus 1 with a standard deviation of sigma square. The minus over here takes care of the fact that these are inhibitory, right? This minus over here. Yeah. So maybe I should say this is all plus but there's a minus I over here. That will be a rather better description. This is all plus, but there's a minus I over here. So that's why you have a minus here, right? But these W, E, 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 I, E are all taken from a normal distribution with mean 1 and the variance sigma square. So let's use that fact. If you use that fact, then we can sum over all of them, right? We can take the Wij's out of the summation, right? So I'll just do it for one of them. You will have Wij EE Uj sum over j not equal to I minus WIP VP EI I giving to inhibitory giving to excitatory plus HV, right? This is the input. This is the this is the input for ith excitatory neuron. So I can take all of these, since Wij are taken from the normal distribution, I can take this as 1. I take it as 1. So I am left with j not equal to I Uj minus I forgot P, and this goes from 1 to n E, this goes from 1 to n I Vp, right? What will this give us? Ne into average of U minus Ni into average of V, right? So U, and there is a bias term as well, right? So that's exactly what we have. Instead of average, I've just kept U and V, right? I have like gotten rid of the angular brackets. So NEU plus minus, did I write? Yeah, minus NIV plus HU, right? Yeah. Question? Yeah.
This, how did you, shouldn't there be something whose distribution is 0, sigma square? Like, shouldn't there be some term like Wij whose distribution is 0, sigma square? Like, because you're
because I'm taking the Wij's from a normal distribution. So this is what this looks like, right? All the excitatories will have positive out degree, all the inhibitories will have negative out degree, right? So since all of them are taken from a normal distribution with mean 1, I am getting like I'm thinking that I don't have the variance at all, right? I'm just saying that it's all 1. So I'm just putting 1 over here, right? All right. So yeah, so U is the average activity of the excitatory units, and similarly you can find it for V as well, right? Now what I have done, now we're going to use the Heaviside function again, which is we are going to get rid of some of the variables. So I'm defining the fraction of excitatory units as F equal to Ne plus Ne plus Ni, Ne by Ne plus Ni. So that's the fraction of excitatory units, right? And so that gives us F into U. You can do this pretty easily if you take if you multiply with, you divide by n and then make it Fu, and then 1 minus F will essentially give you the fraction of inhibitory units. So you have Fu minus 1 minus F into V plus Hu by n. Similarly you can have dynamics for a description for the inhibitory unit as well, right? Now realize one thing, the input is the same for both excitatory and inhibitory nodes. This Fu minus 1 minus F into V is actually the same, which also makes sense, right? And that's what we are seeing over here, is the same, except there is a bias term, but that's okay. The input from all the other units is essentially giving the same value. So this is the mean field which every unit is experiencing, right? So now to dive a little bit deeper, what do we do with this? I'll go to the Lenz Ising model and see how we derive or we use the mean field argument, right? I didn't write easing after, I mean there was easing written over there, but after today's talk I just removed the easing. But anyway, right, so we have this Lenz spin system, Ising spin system, right? And this you should be familiar after yesterday's talk, where ij is the nearest neighbor. And so the mean field approach that we did is we replace the pairwise interaction with the interaction with the field that everyone is experiencing, which is the same field, right? So that's what I did here. Z is the coordination number, which is essentially how many nodes or spins is this connected to, which is the same in case of a regular network. And in this case, in our case, it's essentially capital N minus 1, right, because it's connected to everyone except itself. So Z is the coordination number and M is the average magnetization, right? Now so you can like put this together and you arrive at this. So an energy corresponding to a single spin is essentially, you can see it, right? So each of the spins essentially contribute individually to the energy because it's interacting with the mean field. So I can say the energy corresponding to a single spin as this much, right? Now yesterday I started a calculation but I didn't finish it, which is the Boltzmann distribution for a single spin, right? So if you consider two, I'm just going to give a hint, I'm not going to completely do it. If you consider two configurations where everything is the same, right? So let's say this is one configuration, let's say S1, and this is another configuration which is S2. Everything is the same except a spin flip at a single location over here, right? You can write down the probability of these two vectors, of these two states according to the Boltzmann distribution, right? And using the fact that it's the spin flip is only at this position, let's say k or I, doesn't matter, right? I've used I. So at only at the ith position you should be able to arrive at this expression, right? And if you yeah, so so essentially probability of Si is equal to probability of Si being plus 1 by the probability of Si being plus 1 and minus 1. Okay, fine, I'll write it. I'll write it plus 1 and plus p minus 1, right? And that's what we have over here. Okay, now so here comes the argument is that the average magnetization of the system should be reflected in the average magnetization of the spin as well, right? And so this is what we'll claim, right? So the M was the average magnetization of the system. We'll say that the average magnetization of each spin, every spin, should also follow this M, right? And if you put in the values of SIs plus 1 and minus 1, right, you will realize that you come up with the tan hyperbolic form, which is like e to the power minus beta e minus e to the power plus beta e something like this, right? And that will essentially give you your tan hyperbolic, right? And the minus is coming because SI is 1 once and minus 1 again. You can work this out, it's very straightforward and you'll find it in several textbooks. All right, so and this is what the consistency equation is, right? So let's use it in our model. So we have this mean field which every, like, you know, it doesn't matter if it's excitatory or inhibitory, everyone's receiving this mean field and if you do this, so HU mean field is like this and HV mean field is like this, only this is where the difference is, both of them have the same mean field coming from the outside. Now if you use this particular argument that we did in the lens sizing, what you will arrive at, okay, yeah, right, there's a caveat in the sense that you can use like proper StatMech if it's an equilibrium system. Here, because of this asymmetry in the interaction matrix, you cannot write an energy function, but you can still use this argument of doing a mean field analysis. What you will arrive at is this kind of a equation. Now realize in the previous one we had a tan hyperbolic because the values that they could take was +1 -1, but here we arrive at a sigmoid because the values that it can take are 1 and 0, like u can be either 1 or 0, right. Okay, so the continuous dynamics from this, so right, you can do the same null Klein analysis and you can find the null Klein. So the null Klein will essentially follow Fu minus 1 minus Fv. Since Hu by n, and in the thermodynamic limit this will probably this will go to 0, you can just consider this. So the null Klein will essentially, the point where the sigmoid switches will be Fu minus 1 minus Fv equal to 0. From that you can find the null Kleins, and similarly from here. So both of the null Kleins are very close together, and that's what you see over here. Both of the null Kleins are very close together, and this is the region where both u and v are like they want to increase, right, and on this side both the u and v want to decrease, right, and that's exactly what we see, and that's why the sharpness of this trajectory. We can also do it with the stochastic dynamics, which is using like the switch like behavior. We take each spin and say, like, you know, are you receiving input greater than the threshold, turn on, if not turn off. We do something like this and we arrive at a similar conclusion, right. Okay, now yeah, so here I have essentially shown you the same plot of HU versus HV, and this is sort of the region where you see this kind of behavior emerging. Okay, now if we fix HV to minus 1.0 and change HU, so the external field, or we are sort of applying a current to the excitatory, we see something which we have already seen couple of times: stable, stable, and in the center there is limit cycle. So you keep on applying, yeah. This is, you cannot give an energy, you cannot, you know, give an energy description to the system. Using these two equations, right. This one over here is actually done with the mean field, like I haven't used this. Instead what I have done is u dot. So this equation that we had, we took out all the summations and could express in terms of mean field, but we still had ui dot, right. So what you can do is sum over all the ui dots. So you'll essentially end up with two equations which will have u, the mean field, as a function of u and v, and then v, the mean field, as a function of u and v, and this is what that is. So it's a two-dimensional equation, and this is with just two variables.
What is the stochastic approach?
The stochastic approach is that of the switch. So you have these oh my god, yeah, so you have these, like, you know, many of them together, right. So you take individual spins and say how much input are you receiving. Is it more than the threshold, less than the threshold? More, turn on, less, turn off, right. Yeah, so this sort of a system also shows you this kind of a bifurcation diagram, right. So here one minor detail is the difference has to be order of 1 by n, okay, 5 minutes. Okay, so since we have already sort of said that it can have internal connections, like, you know, thing connecting to itself, let's relax it a bit more and say that the two connections are WV, WU, right. So before we had f 1 minus f, f 1 minus f. Now what I am doing is I am just saying that consider wv and w to be separate, right. We can do, okay, so the steady state will essentially be this, and it shows dynamics like this. So WU equal to 0.3, WV is still 0, right, and HU and HV is 0.5 and minus 0.5, like whatever I have used before. The only addition is W equal to 0.3. So a single self loop of the excitatory gives you an oscillatory cycle. Now why? Let us do the same thing again, like in our linear stability analysis. The Jacobian looks like this. Now it is very straightforward. It looks scary, but if you just do the calculation, it is very straightforward. Now if you find the eigenvalues, now realize the V in, U in, although I have written it here, they at the fixed point they are 0, right. So it simplifies enormously, like this becomes e to the power 0 1 by 1 plus 1 whole square 4. So this becomes 1 by 4, this also becomes 1 by 4, this also becomes 1 by 4, this also becomes 1 by 4. So the calculation becomes extremely simple, right, and that is whatever you have done. And so the eigenvalues of this is given by this. Now notice the minus 1 was the one which was making it stable. Now we have an additional term for in the real component of the eigenvalue, which is WU minus WV by 8t, right. So whenever WU is greater than WV, the fixed point will become unstable, right. So if since I am taking a low temperature regime, like theta temperature equal to 0, that is why you have a Heaviside function. So WU, even a little WU greater than WV is essentially making the eigenvalue positive, so unstable, and that is why we are seeing these cycles. So you can, you can play around with these and see what happens, right. And so this is the same thing. I have varied HU and varied HV, and for each of them you can see that there is a pretty big parameter regime where you can see cycles, and this is only for WU equal to 0.3. You can vary WU and WV as well, but up to a certain limit. Can you see where this constraint also has to be satisfied for it to give imaginary values? So WEU plus WV minus 2 has to be less than 0. Alright, so yeah, this is like we started from a very basic question. We started from a very basic like switch like thing, and then put them together, and you can see that oscillations happen. So I think this is one of the very important papers that had come up, which is a neural mass model of Wilson and Cohen in 1972. They also had a follow-up paper where they did more extensive analysis in 1973, and you can see that they also have these null lines. The ones that here they do not use 0 temperature, but the ones that Pranay was showing today morning, you can see that there is limit cycles, there is also hysteresis, right. Another one which was in the 1990s, 1995, was Ritt-Jensen, where what they are doing is they are modeling cortical column of pyramidal neurons receiving inhibitory and excitatory feedback from local interneurons. So it is like a feed forward network with inhibitory and excitatory feedback, and that could actually show pretty nice features of the EEG pattern. So these are all like you put electrodes in the brain and try to map or see that, okay, I am observing this, do I have a model for that, like how do I model this, I am seeing this, but why am I seeing this, what is the bare minimum required to explain what I am observing, right. So this, I guess, were the founding papers. So some of the recent ones is this particular paper in PNAS in 2021. So it is an experimental as well as a model. They have proposed a LIF, leaky integrated fire based model, and what they do is they have cultured hippocampal neurons, hippocampus neurons, and then they try to study what is the excitation and inhibition interplay of them. And so what they figured out is they change their weights, like they become sparse or they become more dense, so that it sort of balances and you get that cycle. So the assembly of like neurons are sort of self organizing, I don't know if I should use that word, but into something where it will show, like it will be there in that critical state where it will show oscillations. And this is another paper 2 months ago where they have used a very simple model like ours, where they have used some information theoretic approach to say or prove that at that critical regime the information storage is maximum. I do not understand that paper, but I thought if anyone's interested they can take a look. Thanks.